Great. Okay, thanks everyone for coming. I'd like to talk a little bit about clusters, or about distributed systems, which also contain clusters. And the first thing I will start with is a little disclaimer, which is to say that a career in distributed systems is both exhilarating and frustrating. When things work, it's like a symphony. When they don't, it's like an 11th birthday party where half of the kids are on speed. That's a quote by Jeff Darcy, who did CloudFS, and I think it really captures, you know, the sort of daily life experience that you've got when you get deeper and deeper into building evolving distributed systems. So what I've done this year, I had that plan for some time, but this year I really did it. I took a sabbatical. I told all my clients that I'm not available, and for 3 months I went into reading papers, on a stack of papers I had on my list for a long time, so I really could spend a lot of time reading. What happens is, the more you get into this topic, the deeper you get into the field, the more, without you noticing, your sanity leaves you. And you build distributed systems. You're sacrificing yourself for the, you know, for building nice things. So this is just a little disclaimer. I just want to put this here. Don't come to me in 5 years saying, "Hey, you've ruined my life. I know distributed systems now, but that's all about it." I really like that. I like it because you really notice that you don't know anything, or you know some things, but then suddenly you discover you didn't really know. But my name is Manuel Bernhardt. What I do is that I work as an independent consultant. I help companies getting started with distributed and reactive systems. Not only getting started, but also keeping them running. So I either get clients that call me when they get started, they want some training, they want some consulting up front, or they call me and then I need to fly somewhere the next day because everything burns and it's not nice. I'm a Lightbend consulting and training partner, and what I do focus on in terms of technology stack at the moment is mainly Akka with Akka cluster, Akka streams, and basic Akka as well. I do scuba dive since I'm 6 years old. I'm not from Austria, I'm from France, and that's me diving. That's not the Danube, that's that would be too nice, wouldn't it? That is Egypt, which I really look forward to going back to as soon as our kids are a bit older. I don't quite like diving in lakes, there's plenty of lakes here, but that's not my thing, so rather avoid those. So let's get started with a motivational quote, shall we? Life is a single player game. You're born alone. You're going to die alone. All of your interpretations are alone. All your memories are alone. You're gone in 3 generations and no one cares. Before you showed up, nobody cared. It's all single player. Beautiful quote by Naval Ravikant, the CEO of AngelList. So, is everybody motivated now? Yeah? Is that, am I doing a good job? Should I just, no, I think, yeah. No, really what I didn't really intend to motivate you so much as I intended to motivate my talk with this. Because this is something you could replace a human being in this quote by a single node in a distributed system, okay? Because when we think in terms of distributed systems and clusters, when we think about clusters, we think about this. We have these 3 nodes here, and we think we have this God view where we see all the nodes, and we know they're there, and these are the nodes, and this is how it should be. But the reality of things is that when you build distributed systems, you program on one machine. You build things from the perspective of one machine, so what you see is the other nodes, but you don't have a perfect network, so you may suddenly not see the other nodes. And you can't really tell whether you don't see them because the network is down, or because the other node, the other process on the other machine has crashed. You don't know. You can't tell the difference. That makes things quite interesting. So what we're going to focus on today, because I could go on and talk about this stuff for weeks, but, you know, but I had to make a choice. We're going to talk about cluster construction. So that's sort of the foundation. If you want to build a system that sort of pretends to run as though there was just one machine, how do you do that? And it turns out that if you want to do this, you need three things. You need to a way to discover who is there with you in the cluster. When new nodes want to join, you need to know who else is there. You need to figure out when someone crashes, when there's a failure. And then you probably, one of the reasons why you want to have a cluster is that you want to balance load out. Because otherwise you could have just as well run this on one machine. Unless the other reason why you want to have a cluster is for fault tolerance. If one machine goes down, you still have something running. But so this concept of load balancing, of knowing who is busy and who isn't, that's also quite important. And it turns out that there is one simple and very powerful abstraction that helps with this, and it's the one of group membership. So it's about saying, I have this service that runs on every node and that tells me who is there and who isn't. And if we want to go about implementing group membership, we again need three things. We need failure detection. We need dissemination. How do we pass information around as to who is there and who isn't, etc. And then we need a way to reach consensus. So let's get started with this. Anyone knows what album, Pink Floyd album that is?
My first one. My first album.
The first album.
Yeah.
What's it called? That's Wish You Were Here. And I think that is a beautiful representation of failure detection. I don't know why I have a irrational interest for failure detectors and failure detection algorithms. Probably I have that much as stack about just failure detectors papers. There's been quite a bit of research first with synchronous networks and then with asynchronous networks on this topic. So what are failure detectors? Let's start with a little bit of theory here. We have two key properties, let's say, about failure detectors. The first one is the one of completeness, which is to say that if one node crashes, everybody should know about that. There shouldn't be anyone left in the dark as to whether that node is still there or not. So everybody should know that this node is going. It's called completeness. The second property is the one of recursive. And that's about false positives. That is to say, you shouldn't start suspecting healthy nodes of having crashed. That's also something quite important and very important in practice, as we'll see, and very frequent in practice. And then, there is these other properties that we also have to care about somehow. But the speed of failure detection and the network message flow. These are pesky little implementation details that you need to think about when you build your perfectly nice theorems, but in practice they matter quite a lot, especially speed. That's one thing you really, especially if you work with real-time and near real-time systems, you need to know when someone is going really fast. Otherwise you're in trouble. Now how do we go about implementing these things? Well, it turns out that it's not quite something we can do. And this is where we come up with we have our first possibility results here. So in distributed systems research, you can't really prove that something is possible, but you can prove that something is not possible. So what you sort of do is you prove this isn't possible, this isn't possible, this isn't possible, and then you sort of get a sense of where you can go. And so this first impossibility result I want to introduce here is to say that it's impossible for a failure detector algorithm to deterministically achieve both completeness and accuracy over an asynchronous and reliable network. Which is to say, the thing that we wanted to do, well, we can't do it. It's very common in distributed systems. It's usually you end up with sort of this nice situation where then you have to make a choice, so you have to make trade-offs. So we talk about strong to weak completeness, and that's where all or some non-faulty members detect a crash. And then we'll also talk to strong to weak accuracy, and there are no or some false positives. This is a very simplified way of representing this. There is like much more different classifications there. I think there's 12 groups or something like that. And there's been many value detectors put in these different boxes with all of these key properties. But in practice, what does happen when you build applications, especially modern ones, is that the applications, they really want strong completeness. Because the moment you don't have that, things start to become weird and hard to reason about it. So they want strong completeness and they sacrifice accuracy. And right now we're in a situation where many applications or many cluster systems and they use a weaker form of accuracy, but it still has strong guarantees. So for example, eventually there won't be false positives at some point. So you will end up in a stable state eventually, or not, depending on your network provider. If you're running your thing on AWS, anyone uses AWS here? No, good. So Amazon Web Services are, especially the cheaper tiers of computers, are known for having poor network quality, poor link quality. So if you try to build and establish a larger cluster there, it may never happen. I ran an experiment with 400 nodes. It didn't converge in 6 hours, and then that's kind of pointless. So you do need a good network if you want to scale to larger clusters. Well, unless you configure other failure detectors, but with the system that I was trying this on, the failure detector just didn't, that moved. So that's one thing we talk about. So the other thing we do have in terms of definitions is that there is a few strategies when it comes to how you do perform failure detection. The first one is a heartbeat. So one node will sort of send a regular heartbeat out to the other one, and the lack of heartbeat means that there is an issue. Okay. So the fact of not sending information also conveys information, which I find to be a very powerful concept. Then the other thing is a ping, the sort of a typical ping pong. You send something, you get a response, then you have a round trip time that you can measure, that you can feed to your failure detection algorithm, and that's also a very common thing to do. So let's now talk about a few of these real-life failure detectors. They're in the wild. And the first one I want to talk about is the Phi Adaptive Accrual Failure Detector, which is a really cool name, and I think that's why it became popular. Not because of what it does, but because it has this name. So this was Facebook, and they started to use this little database called Cassandra, and they had more and more nodes, and they started to run into trouble because they couldn't keep. Well, these nodes were starting to fail and they couldn't keep this thing stable. So they started looking into failure detector algorithms, and they found this one. And what the Phi adaptive, so there were adaptive failure detectors before Phi, but there weren't any accrual failure detectors. And the idea of an accrual failure detector, so an adaptive failure detector is one that will try to sort of go with the flow of the network. Sort of try to adapt to changing network conditions. If your link quality goes down, it doesn't just start to panic, but it tries to sort of adapt. An accrual failure detector is one that won't just say return a binary result, because previously failure detectors were just saying this node is there or it's not there. You can trust it or you can't. There's no middle ground. So what an accrual failure detector does instead is it computes a suspicion value. And then there is a threshold, which is set. And the threshold sort of is something that the application sets. And so it's the application that decides what to do. So it's kind of, you get a probability back, and then you gamble. And you say, hey, maybe this is good enough. So an example would be, for example, a cluster where you have master nodes and a master node and a few worker nodes. So you could say, I'm starting here. If my suspicion level goes over a threshold of 8, I won't send new work to the node because maybe it's not maybe it has the problem, I don't know. And then when it goes over 10, it starts to rebalance and assign the work to someone else, and then if it goes over 12, okay, this guy is lost, let's remove him from the membership group. So sort of your application could decide with the actual failure detector as to what to do. Now the thing is, if I go back here, if you have this threshold, so on the data centers of Facebook, they're around 6 with the threshold for sort of removing things from the membership ring. The higher your threshold, the slower your detection time. Okay, so if you want fast detection times, you have to take a smaller threshold. Now conversely, because we have to make a trade-off, of course, the lower your threshold, the higher your mishit rate. Okay, and the mishit rate in this case is the number of false positives. So if you set this too low, you will start suspecting everyone. You will never have a stable system. And then there's the sweet spot on 10 and 12 and 14, around here where you have an inflection point, and things start to get better. Now in practice, if you're running on the cloud, I would never go below 12 for this, because the network link is bad. You can't. You will get something, but you would get a lot of false positives with this approach. Another actual failure detector, it has the name is not as cool, it's called the new actual failure. It has a new in it, but that's about it. And this thing, the advantage is it's much simpler to calculate than the fee. The formula is much simpler. It just does a bit of common sense in terms of probabilities. And what I noticed, it performs a little bit better when you run into the cloud. Okay, so in the cloud, you get a slight advantage out of this guy. And I implemented it for ICA cluster and ran a few experiments on it. So it's nice, but it's not something groundbreakingly different, should I say. It's not like, it doesn't give you a big change in behavior or anything. It's still the same animal, but with a slightly different approach of implementing it. So, one of the very nice papers out there is about the swim failure detector. As you swim lazily through the milieu, the secrets of the world will infect you. And this is one of the few, well, not few, many do it, but this cites the paper. It has quite a few references to papers from biology. Okay, so you go and you read the biography, like and it goes into biology. So this comes from infectious diseases, and it sort of reuses ideas from epidemics, viruses, contagion, things like that. And it's not only a failure detector, it has two components. It has the failure detection component, and it has a dissemination component. The dissemination is something we're going to talk about a bit later. And the idea here is to say, well, we want to really scale out. We don't want to have constraints, linear growth of detection times or whatnot. As we grow our cluster, we want some sort of scalable properties. And the way it does this, there's two key techniques. And the first one is that when you start to suspect someone of having a problem, you don't immediately start to take action. You don't immediately start to say, hey, this one's out. You give it a chance to sort of talk back. So one of the things that Swim does is that it gossips. They gossip. And when a node receives a gossip that it has failed, it can go and talk back to everyone and say, hey, I'm still there, come to see me. Which happens in real life. So one of the sneaky things that can happen if you're unlucky in a network, you can have a unidirectional network partition. Okay? So you have a link that fails in only one direction. So that's kind of really hard to work with because you never think in terms of one can see you but not the other way around. So that's one thing that Swim does. The other thing it does, let's show it here. So what Swim will do, it will pick at random another node in the cluster. And then let's suppose that the acknowledgement gets lost. So it uses a ping pong sort of style. It's not heartbeat, it's request response strategy. So either it gets lost, or more commonly the case, it's too slow, especially if you run something with Java, garbage collector. Sometimes the garbage collector says stop, and then you can't do anything for some time, and then everybody thinks you're gone. So that's why it's really important to look at allocation rates and things like that when we build a distributed application. It makes a lot of sense during these days. So your app gets lost. So what does Swim do? It will send a ping rect. It's a different kind of message to other nodes at random, and they will in turn start to ping that node. Okay? And now this node replies to someone, which then relates to the first one, and we know that it's still there, and it's just, so end of the day, it's safe. Now, that's Swim, which is from 2001, I think, or 2002. And it turns out that in practice, in today's world, in today's data centers, Swim still has a lot of false positives. And that's not good, because false positives means that you go up and down, you're flaky, you don't know what to do. So there comes Lifeguard Failure Detector, very nice name. Evolution of Swim, a few extensions to Swim. And that's a little company known as called HashiCorp. You may know them. They do things like Console, like Terraform, Vault, all sorts of operation-related products, many open source things. And they extended the Swim protocol. The implementation is open source. It's written in Go. And what's really nice about it is this, if you look at this is L0, that's Swim, it's vanilla Swim. And then they have these extensions here, and when you combine all of them and you run that, you have less than 2% in terms of false positives. Okay? False positives at unhealthy nodes and at healthy. It's crazy, it's really, really good. It really drastically reduced the amount of false positives. They did with one of the, I think it was L2 or 3, did a few, so there is more network load on this guy with one of the optimizations, but it really pays off. So, what they argue is, well, we now have InfiniBand everywhere in our data centers, so why care about bandwidth so much if stability is what you want. And I haven't found anything more recent so far. Maybe something popped up since March, I don't know. But this is as far as I got in terms of state of the art and in terms of failure detection. Okay, so that was about failure detectors. Anyone knows what that album is?
Dark side of the
Poles. And I found poles really a nice one for dissemination. How do you pass information across? Put it out there in the class tab. So what do you do with dissemination? Well, how do you communicate? How do you talk to one another? How about members joining, leaving, failing? How do you disseminate this information? So one strategy might be multicast. And that's one tweet by Kenny Fournier. Just saw the phrase multicast support, and a chill went down my spine. And then we have here the almost uniform inability to support multicast on today's networks. Such a humiliating defeat for distributed systems. And that's really the sad state of multicast in today's infrastructure. Is we don't have multicast. We just don't have it. This is it happened to me a few times. You go to the client and so what about do people multicast? No. We went to see our network guys, and they stared at us in a very angry way, and then we crawled away. So it turns out system operators, infrastructure people, they don't want to enable this stuff. It's not good enough. I don't know. And in general, it's just. It's not really available. People are not willing to do it, except in some cases, except in finances and do that a lot. But it turns out that it's not something you can easily get. Even when you get it, then there are other problems. The moment you have multicast, you have another set of challenges that comes in terms of ordering, multicast ordering, delivery reliability. There's a very nice study on, if I go, total order broadcast and multicast algorithms. So this is a survey. It's 67 pages. I read that. It's full of algorithms for sort of figuring these things out. Very interesting read, but still not something. I think we're not ready. Let's see where it goes, but we might need a bit more time for that to. So what do we do? Well, who remembers Napster? Kazaa, etc. So the good old days of peer-to-peer. That's where the foundations of what we do these days in distributed systems in relation to gossips has been developed. Because we take this idea of a peer-to-peer network, which forms a big ring of people, of computers on the internet. You're not gonna, if you search for something, you're not gonna go and talk to everyone individually. It would take ages, right? So what you do is you use search protocols like Quord or others that sort of employ this gossip, transferring, spreading information via gossip through the cluster, okay? And then what happens, you get much better results, because if we look at it in practice, so one of the oldest and most popular ones is gossip, random gossip. So it is only one node, you only gossip to another node at random. T0 here, we have 1, T1, we have 2, and then T2, we already have the whole cluster here. So this goes really quite fast. You don't need to talk to that many people. This is sort of really, this spreads out really well. You have other styles, round robin. So these styles try to be more deterministic so that you could make some assumptions and calculations as to who is now getting or who should have received your message by a certain round. Turns out this has not really been picked up by anyone. Everybody still goes with random gossip. Nobody uses round robin or binary round robin, or even the fancy one with sequence check, where you can sort of assume that now everybody got it. Not being really popular. I don't know why, but it exists. And then another one, very nice, that's Swim again here. I talked about diseases and infections. And this is called infection style gossip, because what it does is, you remember that there is ping messages, ACK, ping rec, and what this does, it just piggybacks on these messages, because you're sending out a packet here, but you say ping is what? That's a byte. So it's not very much, right? So you still have a lot of space there on your packet that you can fill. And then you fragment your gossip and you spread the gossip around using that. That's a very elegant technique I found, because so in Squid they don't have a dedicated gossip protocol, like where they don't gossip explicitly from one node to another, where they do every second they go to gossip and talk to other people. They just use the failure detection protocol and infect that one with their gossip. So very nice as well, I found. But that's just Swim and Lifeguard can do it. Many other stages go for random gossip, which works really well. But what do you do then? What do you gossip about? Well, let's look at the original paper. Say I have a node A. I am the node A. So I have seen myself the last time 0 seconds ago. Now the node B has seen the node, we have seen B 1 second ago, and we have seen C 3 seconds ago. Now we have a node B, which has seen A 3 seconds ago, which has seen B 0 seconds ago, because it's B, it's always there. And then it has seen C 1 second ago. When they exchange their gossip messages, you merge the gossip and you get a table where it says A 0 seconds ago, B 0 seconds ago, C 1 second ago. All of these things are helpful. In this failure detection protocol, gossip-based failure detector, you then set a threshold, and you can say, for example, if one node goes over 5 or 8, then it's dead. And then, since it spreads across eventually everybody will know that it's gone. You don't even need to do anything special. You don't have to go and sort of stuff. So, And I could go on and on about this part as well. Now let's talk about gossip optimizations for a moment. What Akka Cluster does, which is very nice, it keeps Akka Cluster in its gossip message. It keeps a list to all of the members that have seen this version of the gossip. So every time someone passes it around, it sort of adds itself to the list and sort of continues. So with that in mind, when you're in node and you're about to do the random gossip, you will do it totally random. You will favor a node in the cluster that has probably not seen the gossip, because it's not in the list of members that have seen the gossip. You then know, okay, maybe this guy hasn't seen it, so I'm going to talk to him. I can cluster again when it starts up, a large cluster, or when it starts up, when less than half of the members have seen the latest gossip. So that's when you start up, or when you just had a network partition and you're trying to recover from that. It speeds up. It gossips 3 times as fast as your normal gossip interval. Normally you would gossip at once a second, and in that you do 1/3 of that, and then the gossip spreads faster, and you heal faster after a partition, and you start up bootstrap faster. Lifeguard, it has a very nice entropy mechanism where it says, we're doing all of this via UDP, because that's what Lifeguard does, and we do all this little gossipy stuff, but that's creating, second law of thermodynamics. That's sort of not going to work out well. So what they do is they introduce this entropy mechanism where you do a full sync. One node picks another node at random in the cluster once in a while and does a full sync via TCP. And that way you sort of have a better cohesion. You reach convergence faster than if you left everything to random channels. Eventually, yes, it will propagate, but it will take longer. Especially if you have a network partition or something like that, you will take it. All right. So here is one very nice album as well. Anyone? Yes. That's consensus, which I find is yeah. I don't want to talk about it. I want to talk about it, but anyway. Let's start with what is consensus? Well, we want to agree on something, but with distributed systems, so how we agree on things. And let's start with an impossibility result. So here we are looking at this. I don't mean to look at the entirety of consensus protocols, and I want to look at the ones that are interesting for building a cluster. And it turns out that it's group membership with a single group, so a primary group, primary partition, is impossible when there is at least one node that is suspected of having failed. So in other words, we can't have it. We can't have the illusion of group membership. Or we can, but not always. So this impossibility result and the previous ones are based on a very important one called FLP, impossibility result. FLP is from the names of the authors of the paper, and that one is about saying you can't reach consensus. You can't have a consensus algorithm in this system the moment that you suspect one node of having crashed. For a very long time, people believed, when I say people, I mean researchers believed that you could sort of pretend that you could remove that node and sort of say, hey, we know Joe is gone, let's all pretend Joe is gone. But what turns out is that that doesn't work quite as well, because maybe it's not Joe that's gone, maybe it's everyone else that's gone. And it's been proven, so that's impossible. So what do we do? What does it mean? It means that if we will want to have a membership service, it would be unwise to make membership-related decisions while we suspect processes or nodes of having crashed. Let's not change our membership. Let's not start tinkering with our membership ring so long as we have suspect members. That makes us, that makes things a lot harder. And now what I want to do is I want to go a little bit through consensus fundamentals, which will get us there. And like, how do we do this? So the first one is for reaching consensus is time, because often that's one of the fundamental things we have to agree upon. And we can't quite agree on time in a distributed settings just because things are distributed, so time is not the same. That's sort of basic physics, but still. So one important result here, one important paper. So if you come out of here and think like, I want to read a bit more about this, there is one paper you should read. If you are going to only pick one, pick this one. Leslie Lampworth's Time Clocks and the Ordering of Events in a Distributed System. Paper from '78, and that's sort of really still the foundation of very many things. We still use this a lot, and that introduces the concept of a Lampworth clock. And a Lampworth clock is basically a logical, it introduces the notion of logical time, and sort of the idea is how do you order things, events, in a distributed system? How do you define something happened before or something happened after something else? Because, you know, they happen on different computers, so how do you order them? So that's the idea of Lampworth clock. So now we can order events, but it's not enough, because it turns out that with Lampworth clocks alone, you can't tell when two things happen at the same time. Okay, you don't have a notion of conflict or a notion of the same. So what you have is vector clocks, and vector clocks are just vectors of Lampworth clocks. And what you get then is the semantics of concurrent events. And now suddenly you can do very powerful things. You can notice that two things actually happened at the same time. There is a conflict, you have to merge them, you have to reason about them. And then there is two other things. They're called version vectors and dotted version vectors. And if people always mix these two up, there is even a blog post that is called Vector Clocks Are Not Version Vectors, or the other way around. The semantics of vector clocks are about events, and the semantic of version vectors and dotted version vectors is about order in replicas. So where you replicate things, where key value stores, where you have many nodes that want to replicate the data across all the nodes. So that's where you go for version vectors. Dotted version vectors are just better version vectors that don't have as many false positives that sort of say, hey, these things conflict, they don't really conflict, it's just the logic was not right. And you know, for the moment I just talked, but I haven't shown you in any way or form that this stuff is real and makes sense. So let me show you a bit of code. So it's just a definition of it. It's even Scala code, it's even better because so this is the gossip definition, the gossip class in Akaclasta. We've got our members here, overview, and we have a version of the gossip, and that is a vector clock, okay? So as Akaclasta spreads its gossip around, that gossip message has a vector clock. And then when two gossips meet, when two nodes exchange their gossip, like I receive the gossip from another node, I'll be able to look at that with a version clock and a vector clock. And the vector clock will tell me this happened before, so I can discard it and send the other guy the newer version. This happened after, okay, cool, I have that mine. Or this happened at the same time, and it's the same, so, well, we don't care. Or this happened at the same time, and it's different. So now I have to merge these two gossips. This other node has seen things that I have not seen, and vice versa. So now I have to combine these two things. And I could go on and explain what tombstones are and so on, but I think they would run out of time, or I can come back to it later. But just to say, vector clocks are real. Now the second thing we do, the second basic thing we do, if we want to reach consensus, is we want to have a replicated state machine. Any sufficiently complicated mod class contains an ad hoc, formally specified, bug-ridden, slow implementation of alpha state machine. Very nice quote by Pink Floyd on state machines. Anyone has used state machines or uses them on a daily basis? I hope you all do, because they make things a lot simpler than just going around. So I recently am working a lot, so I'm working really a lot with state machines. I can define a few state machine facilities and I'm using that a lot. 80 projects. So again, it was Lamport in his really important paper. He introduced in that paper the notion of a distributed vector, replicated state machine. So how does that work? Well, this is my client here. This is my browser, or I don't know what. And this is my replicated system. And what I want to do is I want to store something in a safe fashion. I want to store the same value, but I want to store it on 3 nodes because, if one dies or 2 dies, I still want to keep my data safe, right? So what I do is I send my events up here to one of the nodes, because I only talk to one server. These are servers specified. And then this one will send these events attached with a vector clock to the other nodes. So we know the order. So we know the order, and what we do then is we apply these events in the same order to a state machine, to the local state machine of the server. And since we have applied the same events in the same order on all state machines, we now know that the state is exactly the same on all three places, okay? We know that, we have proven it, it's a guarantee that we have. And that's it, that's a very simple but very powerful concept. Now it turns out that as simple as it may sound, look on this little animated thing here, it turns out that in practice it's not as simple as that. So what you have is, anyone familiar with Paxos? Heard the name Paxos? Raft? Cas Paxos? Oh, that probably nobody heard. I guess so. So Paxos comes from this paper, 1908. Leslie goes and says, part-time parliaments. That's the first, how do we implement these things in practice? This is an implementation, like a specification of how to implement a consensus protocol. Then at the conference in 2001, people complain and come to Lamport and say, I don't get this is too difficult. So he sort of comes and brings a few people about it, explains it again. And then he goes home and he publishes Paxos Made Simple, 2001. And then, 13 years later, in 2014, we get the Raft paper, which is called In the Search of an Understandable Consensus Algorithm. Which is to say that even Paxos Made Simpler wasn't that simple or simple enough. And even when you read Raft, the design goal of Raft was to make it an understandable and teachable consensus protocol. Okay, so they really, and even if you go into that, that's still hard to understand. Okay, Raft is still not hard. Still, you can get it wrong. Many implementations of Raft have bugs because people forgot about this or that. And if you look at Raft as well, you have a single leader. It's not okay. So anyway, there is many ways in which you can get it wrong. It's still not that. And then there's a very nice one here, Cas Paxos, compare and sweat Paxos, which uses one of the things of Paxos, one of the definitions, the simpler ones in which Raft takes a few ideas. But anyway, Daniel Bristow did that, and that's from March. Okay, so as I was researching things, this pops up. Yes, something new. So if I take another sabbatical, I want to implement this one for Raqqa. In the meanwhile, it sort of has no leader. It has no logs. Sorry, so it makes do with a lot of things. It's a lot simpler to implement, and it's quite nice. So this is sort of replicated state machines. How do you take back one value and make sure it's the same everywhere? Consensus everywhere, okay? Now that's the old school, should I say, of doing consensus. Then there is a new school, and they have a cool name. They're called CRDTs. Conflict-free replicated data types. And as the name can tell, like conflict-free, what does that mean? Is that, well, we will never conflict. We shall always be able to merge. So there's two families. We call this strong eventual consistency because we know we have a strong guarantee that we'll be eventually consistent. So as soon as everyone is there again, we'll be able to catch up and sort of spread agree on the same value. There's two families, commutative CRDTs and CN RDTs and CV RDTs. So commutative, they sort of rely on the commutativity of operations. 2 plus 1 equals 1 plus 2. Plus is commutative, so you can stop things. Turns out that if you want to implement that, you need reliable broadcasts, okay? Because you need to pass, it doesn't matter if you're commutative, it doesn't matter if you're commutative if you lost one of the numbers, okay? So you need a reliable broadcast, that's not easy to get. And then the other thing, the other family, the other part of the other family is using conversion of states. So this one uses a merge function, which is monotonic. Monotonic means you only draw in one direction, either you go up or you go down, but you don't go like this, okay? You only go in one direction. So what you have here, for example, our merge function is the max, okay? We have 3 nodes. We start with 0 on each node. On the first node, we set our value to 1. On the second node, we set it to 4. On the third node, we don't do anything, we use it 0. Now we broadcast our value. It goes down to the third node. So that's the maximum between 4 and 0. It's going to be 4. Then I also come and broadcast my value 1 here to the third node. That's the maximum between 4 and 1. It's still 4, so I get 4 here. Here I also broadcast down, it's not shown, to the second node. It's the max between 1 and 4, so it's still 4. And then here we have the max between 1 and 4 again. It's 4, so at the end of the day, we have 4 everywhere. Okay? And I haven't had to do much there, just broadcasting. So it's just, and there's very much active research on this because people keep on inventing and discovering new CRDTs. It's a very active field of research, very interesting, and it's employed in many systems already. Really helpful when you've had a network partition to recover. Akka cluster uses it. The gossip I showed you, it's a CRDT. So when there is a conflict, when the vector clock says, hey, it's the same, it sort of merges, not sort of, it really merges, and since it's a CRDT, it can merge, it always converges, it always is able to come back on its feet. Now, my favorite way of reaching consensus is by convention. So one of the things we could do is we could not transmit information, so the heartbeat I was talking about. We convey information by not conveying, by not sending anything. That's one thing. And the other thing, which I find quite elegant, is Akka cluster's leader designation. So Akka cluster has a leader concept. The leader is the node in the cluster that makes a decision. But it's not elected, as you have in other places. There is no votes or anything. It's just the nodes, they all have an address. Okay, IP address, network address. And then Akka cluster takes this list, orders them by address, puts the ones that are not in the right state for being a leader down at the bottom, and it takes the first one. So the first leader, the first node is the leader, like I mentioned. And what it means, I find it very powerful. What it also means, as we'll see, is we can't make this, the leader can't make decisions when there is a failed node. To come back to the impossibility results from before. So this was a sort of a quick stroll through 3 of the foundational aspects for building things. But now I want to talk a bit about this thing in practice as well, with the time that's left, to show you that this is a real thing. So, Akka cluster, it uses the phi adaptive accrual failure detector with a ping pong strategy, so no heart beating, but ping pong. It uses a different implementation than the one in the paper that's tuned, quote unquote, for the JVM. what the JVM does, it goes garbage collection. And stops the So what phi does, what the Z implementation does, is basically introduces a shift in one of the calculations of phi. It just shifts everybody for 3 seconds by default, so that it could survive missing 3 heartbeats in case of a garbage collection, but that's sort of really bad in terms of the speed of detection. So that's why I say adapt. So it's one of the things where I think there is still quite a bit of potential for improving in backup. It uses random bias gossip with an 80% probability to nodes that have not seen the latest version of a gossip, or when your node is larger than 400 members, it goes down to 60% probability. It also changes quite a bit of things when you reach more than 400 nodes on your cluster. It sort of changes its properties. And the consensus it uses for membership, well, it has a leader for convention, and this leader takes all the membership decisions. So when anyone wants to join, they can go talk to any node, in theory. They will go in practice talk to a seed node, which is an advertising node. But it's the leader that has the last say that says, yes, now you're up, now you're part of the family. Same thing the other way around with removal, but instead of just saying it, let me show it to you. Before I go there, this is ICAP cluster, the membership layer, basis. And then you have a lot of things on top. You have distributed set data, these are CRDTs, CBRDTs at the moment. Cluster singleton, which is about having one thing in this whole cluster. If the node in which the singleton runs it is automatically reborn on another node. And then you have sharding, where you run many things, and you sort of shard them across all your cluster nodes, and if that one node dies, the shards get reborn on other nodes. So pretty cool, some of this you build your application. Now, this is the membership transition diagram, the states through which a cluster node could go. So let's look at the happy path, okay? I'm joining, I want to join, I'm joining. And then the leader says, yes, now you're up. It will do only so once when the cluster has converged, when everybody has seen the latest version of the gossip, then it lets new people go up. Then you want to leave, so you're in a leaving state. Then again, the leader says, now everybody knows the latest version of the gossip, and it's a safe moment for you to leave. So now you can leave, and you're exiting, and then you're removed. And that's the sort of theory, and then the real life looks a little bit different. Sort of a sad path where you're joining, you're up, and then you're unreachable. And it's not really a state, this is a pseudo state here. That's why it's not a rectangle, it's sort of this thing here. And it's not the leader that says it, that's the failure detection, that's phi that tells us you're now suspected. You're unreachable. You can go back to up, huh? If it was a false positive. It's not like a terminal state, but you might stay there for a moment. And then, now if any node is in this, nobody can transition here, and nobody can transition here. That's kind of annoying. Especially if the node is really gone, you can't make a new one, okay? You can't have a new one joining. Suppose your JVM crashed, and you want to join again, you can't, because the other nodes, they still see you in that unreachable state. So what you have to do is you have to transition that node to down in all the other nodes. You have to tell every other node, or the leader at least, down. But who is doing this? It's not the failure detector, it's not the leader. So who does this? Well, that's where, that's unicorn land, that's where the magic happens. And that's the very nice and interesting space of split brain resolver algorithms. So that's where you make an automated decision as to which side of the partition survives. So if it's only one node that just crashed, okay, that's, the interesting thing is when you have two-way or three-way partitions. Who is going to stay there? Who is going to make it? There's many different strategies. I just reviewed for a client all the open source implementations of the ACAP split brain resolver out there. None is correct. 5 or 6. I have one, but I'm not giving it away. I mean, I'm not open sourcing it because otherwise Lightpen would not be happy. It's one of the commercial offerings of Lightpen to sell that thing. And if I start to open source my thing, I wouldn't be. I'm a Lightpen partner, so I can't really. So, the thing is, I fear that we are out of time, so I won't be able to tell you about how these things work exactly. But I do intend to write about it a bit more on my site, so if you want to go there on the blog, I do intend to write more about these things over the summer, I hope. I do find some time. This is the list of papers that has been misused from this talk, and that's pretty much it. Yeah. Thanks for listening, and do you have any questions? Yeah.
You mentioned before you had trouble with ABS.
Yeah.
So, did you get any better results with the other ones?
Google GCP has a nice network. And AWS, when you give them a lot of money, you go to the M1 and M2 instances, or C2, the ones where you pay a lot more, you get in a up in a different network category. Okay, so suddenly the networks are even better. And then what you also can do with the more expensive AWS instances, you can use placement groups. And then instead of being spread out in your data center and any rack anywhere, you can collocate them on the same rack. And that makes more sense if you build a cluster. Yeah. But GCP has a better network. They have atomic clocks in every data center, and then they have GPS on every rack. They're really crazy. More questions? Anyway, I'll be here for a bit still, so okay, on to this, and thanks.
First, you could move forward, so I would like to present you.
Okay, thank you. Thank you.
Okay, we have a break now.